So for coding again, we will go on to MATLAB Octave like coding. So I'm doing this coding on Octave and I have already written these codes. So we will first of all see the output and then we will understand what this code means. So let me run the code first. So this code F, on running it, I get these outputs. So now what are we going to do here? We have two outputs here. So first of all, let us see the first output. This is the frequency modulated signal. It's very dense graph, so it's not very easily visible. So let me zoom a portion of it. So I'm zooming this portion of it. So you can see here, I'm further zooming it. So let's take only this much portion. Now you can see here the effect of frequency modulation on the carrier. You see that somewhere the lines are very dense and somewhere the lines are not dense at all. So this is what we mean by a frequency modulated signal. So these high frequency regions, they are symbolized by this densely populated region of these lines, and low frequency regions are the regions where you do not see much density. So this is the first thing that we have obtained. So I have created a frequency modulated signal by using the general equation for frequency modulation, which was this. So this was the equation which we were using for frequency modulation, and we have only used this particular equation. We have used this equation because by changing the value of kf into mt, we can use it as NBFM, or by taking kf into mt much higher than 1, we can use it for WBFM. So we have used this equation in general, and by using that equation we have got this plot. The second plot that you see here is a plot of two signals. You have got message signal and you have got demodulated signal. So message signal is shown in blue color and demodulated signal is shown in red color. So this has been obtained after the procedure of differentiating and then applying the envelope detector, and you can see here that these two signals seem to overlap perfectly, and only at these beginning and end points, because of the abrupt truncation of signal, the matching is not there. But in general, if the signal is of very large duration, you can expect that these signals will overlap for most of the time. And one important point to note here is it is not necessary that these red and blue signals should overlap exactly. I mean, red and blue signals, they ought to have same frequency. It's not necessary that they should match in magnitude also, right? So for an example, this red signal could be sine of omega t and the blue signal could be 5 into sine of omega t. So only there will be difference in amplitudes, but the frequencies will remain same. So that output is also acceptable. And in the output, there might be some DC term also. Although, in my coding, I have removed the DC term. So it's not necessary that if both of the signals will have this DC value equal to 0. So DC value can easily be removed by using a capacitor in your hardware circuit. So these two changes in the signal could be there if you see the output for yourself by running this code for different signals. So amplitude variation and a DC component. So these two signals can differ by that. But for my coding, I have removed that effect, right? So now let us go to the code. We will understand each and every line of the code. So this is for FM demodulation for FM wave, right? So section 1 is about naming. Section 2, let's look at section 2. It is the usual section which is used for creating the time and frequency axis as per the sampling theorem. We have discussed this several number of times. So let's move on to section number 3. Here we have defined a message signal with amplitude AM. So AM is the amplitude of message signal, FM is the frequency, and here your message signal is defined. And in this section only you have also defined the value of KF, right? So kf into mt, that is am here. Kf into am will be the product will be used for designating whether the signal is nbfm or wfm, and in this particular case you can see it's wbfm because 250 into 10, which is 2500, is very greater as compared to 1. So now message signal is defined. Similarly, carrier signal is also defined at frequency 100. The frequency of your message signal was 2 and the frequency of your carrier signal is 100. So this is defined in that particular way. And after that, you have performed the simple frequency modulation using the equation that we have just discussed, this particular equation. So this equation is applied. We have already done this several number of times. So you can see this complete equation here. and this is the frequency modulation. After that, now the important part comes. After modulation, suppose that you have received the signal at your receiver, and we are also assuming for the present case that there is no noise, no amplitude distortion, etc. in the signal. The signal is received as it was sent from the sender. So in that particular case, we now differentiate the signal. So for differentiating the signal, you have this command diff. Now this diff command will differentiate your signal in such a manner that it will take the difference of two consecutive terms, right? So if it is calculating the value of the first term as derivative, it will subtract the first term from the second term and it will give you an answer. Similarly, for the second term, it will subtract third term from the second term and give you an answer, right? So that way, because that's what we mean by differentiation, and since we have a discretized version of the signal, so here we have the derivative of signal. Now two important points to note here are the difference between these two signals should be divided by the time gap between them. So the time gap is capital T. So you could also use a divide by capital T sign, divide by capital T here also, because capital T was the gap between two consecutive samples, as we saw while creating this sampling theorem. So this capital T could be divided here, but then that division would hardly affect your results here, because ultimately you are interested in relative values, so derivative is there, so you can use a divide by T also here. And another important thing is, when you take the derivative through this diff command, your signal will reduce in size by one sample. Why? Because for the first sample, if you calculate, you have the difference between the second and the first sample. For the second sample, the difference has to be between the third sample and second sample. For the last sample, if you will calculate the derivative, there is no point from where you should subtract the current value. So that is why it will not be calculated, and that is why I have appended a zero with my signal. So zero can be appended at the beginning or the end. If the signal is of very long duration, it hardly matters where you append this zero, either at the beginning or at the end. So I have appended it prior to this signal, and that is how the length of the signal remains the same. So this line is done for that. And then after, we do envelope detection. Now envelope detection, how is it done? There are various ways of doing envelope detection. One such way is you just square your signal. That is, you make your signal positive, you have squared your signal, and then you just take that signal in frequency domain, right? Because what we want to do is, we have just squared our signal, the signal that you have obtained here, this graph that you see here, this will be squared, so every term will become positive. And after that, we want to apply, a low pass filter here, because that low pass filter will only take this envelope, these high frequencies will not be taken up there. So low pass filter has to be applied. So that is how envelope detection is done. First of all, you square the signal and then take a low pass filter and use some cutoff and get your low pass signal there. So you just bring that signal into frequency domain by this particular command. This is a very easy command of FFT and FFT shift. Then you design a low pass filter in a way similar to what we have already done in various other codes. You take the low pass frequency here, which is 1.5 times of FM. Now FM is the frequency of the message signal, and instead of taking the low pass frequency as at exactly at FM, we take some margin and we made it 1.5 times, right? So this is a tunable parameter, we will talk about this later. So this 1.5, you could also have taken it 5, it will give you a better signal, but then again there are some criterias to use, so we will talk about it in the second code. Then you design your filter. First of all, you have designed the length of the filter equal to your frequency scale. Then this is the equation for filter. That is, your response should be 1 from minus of low pass frequency to the greater of low pass frequency, so that your filter is constructed here. Then you filter your signal by multiplying this filter in frequency domain with the derivative of FFT here. And after receiving the signal, that is filtered signal in frequency domain, you bring it back to time domain by applying IFFT and IFFT shift commands. You have brought back the signal which was in frequency domain into the signal in time domain, and then you also subtract the mean of this demodulated signal from the original signal, because I have talked about a bias in the output. So to remove that bias, you could do that, but this is not necessary because I have done this for a better visibility purpose. And in hardware, there will be other ways to remove that bias. You could apply a capacitor there, it will do the same operation. And sometimes it is not required to remove the bias, right? So this is not a necessary step, but for better visibility, it is there. Then there is this plotting logic. There is nothing to explain in plotting logic. It is simple plot command here. But the only point that I want to emphasize here is when I have plotted the graph, I have used a factor of 60 for multiplication with the demodulated signal. Why? This factor of 60 comes from the fact that when you pass your signal through various filters and various modulation and demodulation processes, a lot of energy is lost by this operation of filtering and sending your signal over channel and modulating it, etc. So at the output we need an amplifier, and 60 is not a specific number that has to be used, but then you can use any number of your choice. I have selected 60 just for the sake of making those two plots looks exactly the same. So if you run this code now, you can see the output here again. Now your FM signal was this, which I have already shown by zooming here. So you can zoom some portion and see the result for yourself that it looks perfectly FM signal. And then after, in the second graph, if you see, your both of the signals, they match perfectly. The red and blue signals, message signal is the signal that was actually sent, and the red signal is the demodulated version which we have obtained after differentiation and then envelope detection. And this red signal is also adjusted for a bias and its amplitude variation. So we have applied an amplifier up by a factor of 60 there, and for removing the bias we have used subtraction of mean value of that signal from itself. So it is matching perfectly with this, but otherwise also it is okay, right? So now this was for the case of tone demodulation. By tone demodulation, we mean that the modulating signal to begin with was a sinusoidal signal.